infinity, an idea that shakes the mind. When we try picturing an eternal space or time with no beginning, it immediately disorients us. When you look up at the night sky, that feeling only gets stronger. The stars stretch out in every direction. There is no visible wall, no apparent border. Because we can't see an edge, our brains naturally assume the dark goes on forever. This diagram shows a 93 billion light-year span, the maximum distance light traveled since the universe began. Space extends further, but not forever. Cosmological models describe a curved universe. You travel continuously without hitting a wall, yet total volume remains finite. We know the cosmos is unimaginably huge, but in the physical sciences, a massive volume is distinct from an infinite one. We have never measured an endless expanse. Every piece of reality we can verify is defined by vast but strictly measurable limits. We tend to apply that same endless thinking to time.
It feels like a ceaseless flow, something that has always ticked backward into the past and will always tick forward into the future. Physics describes a different reality. Time had a distinct starting line. About 13.8 billion years ago, space and time came into existence together during the Big Bang. Time itself was created in that outward pulse. Because of this, the concept of before has no physical meaning. Looking forward, the future of the universe is also bound by physical laws. Whether it expands until it slowly cools into a heat death, or gravity eventually pulls everything back together in a big crunch, the lifespan of the universe is a quantifiable duration. Time possesses a specific birth, and it progresses as a measurable duration. We can calculate immense spans of billions or trillions of years, but we cannot find an eternal clock. Time is firmly bound by scale. Classical physics once assumed you could take a physical object, say a grain of sand, and cut it in half over and over again, endlessly. We know now that there is a stop. Slice that sand down to dust, the dust down to molecules, and the molecules into atoms. Break apart the protons and neutrons inside those atoms, and you find indivisible particles called quarks. This animated diagram illustrates the absolute bottom of reality, the Planck length. At 1.6 times 10 to the negative 35th meters, continuous space completely breaks down. Below this threshold, reality becomes quantized into tiny, indivisible grains. You can no longer measure coordinates, trajectory, or duration. Energy operates under the same strict boundaries. The first law of thermodynamics dictates that energy is conserved. It is transformed, not created or destroyed. Because it is strictly conserved, the total amount of energy within any closed system is always a constant set amount. The universe is built on a quantifiable floor. Matter and energy are subdivided into specific, finite packages that cannot be further diluted. Beyond the scale of matter, quantum mechanics introduced a shift in how we understand the universe. The observer is an active physical participant in the system. An unmeasured particle exists in quantum superposition, a mathematical blur of multiple states. These probabilities collapse into a defined reality only at the moment of measurement. In this context, an observer is simply any physical interaction between two distinct systems. A detector, a photon, or another atom bumping into a particle acts as an observer, forcing the system to take a defined form. This animated diagram demonstrates why absolute properties don't exist in isolation. A particle cannot have a position all by itself, but when a second point appears, position, distance, and time are born out of their relationship. Every observation assigns a specific value to a system. Since a measurement is, by definition, a finite number, an infinite value cannot exist within the data we use to describe reality. Reality exists as a web of correlations. From mass to position, every property we observe is born from a relationship between distinct finite systems. It is tempting to think that if you remove all matter and energy from a space, you would finally be left with a true, endless void. But a perfect vacuum does not exist. The quantum vacuum is a field governed by zero-point energy. In this seemingly empty space, virtual particles briefly flash into existence out of the field and extinguish just as fast. This background activity is a real, measurable physical phenomenon. Yet even this energy operates within strict thermodynamic limits. It never grows out of control or extends without a measurable value. Even the absolute emptiest pockets of deep space are governed by strict numerical boundaries. If nothingness itself is held in check by quantifiable limits, infinity cannot be found in physical nature. If physical reality is strictly finite, we must look elsewhere to find the source of our fixation on the concept of forever. Infinity is a mathematical tool, an abstract shortcut that allows us to build equations and model processes that push past the limits of our experience. It works beautifully on a chalkboard, but it remains a logical idea, not a physical destination. Our minds can picture a line stretching without end, yet the very consciousness picturing that line is produced by a finite number of neurons and electrical impulses. Our most limitless thoughts are generated by a bounded biological machine. We often mistake limits for imperfections, but they are the exact mechanisms that provide structure. The fact that energy is conserved and time is measurable is the reason reality is stable enough to form stars, planets, and life. A bounded universe creates the stability required for stars, planets, and life to emerge. This structured, finite nature is what allows the cosmos to be studied, understood, and known.